So there is a small number of strong bases, therefore weak bases are more numerous. And weak bases, similar to weak acids, are weak electrolytes and vary greatly in their strength. And it's all going to be based on the amount of OH minus that they produce in solution. Therefore, equilibrium calculations, just like those with weak acids, are going to be used to help us quantify the extent of the base dissociating. Now let's think about it. Technically, a base does not dissociate, right? It's going to accept a proton. But the fact that it's accepting a proton is allowing the other species to dissociate, so they still just kind of keep that term. Okay, folks? Now, what does that mean? It means we're going to have a Bronson-Lowry base, just like we have here, and you're going to mix it with water. This Bronson-Lowry base is going to accept, and remember, it has to have a lone pair as well. It's going to accept a proton from the water, which is acting as an acid. Then you're going to end up creating the conjugate acid of the weak base. And of course, you're going to form OH minus. So the more OH minus that you form, that's going to give you the relative idea of a strength of that particular base. Now, the cool thing about learning about bases, in my opinion, is that we've already went through so much learning about acids. And so we kind of just understand, oh, we already know there's an acid dissociation constant. We already know the values we can get from that. We've seen like equations and we've been through equilibrium problems. And so it allows us to kind of not just blitz through, but allows us to just layer the information for weak bases a little bit easier. So that means we can take our weak base mixed with water equation or reaction here, and we can get our Kb value. B is going to stand for our base dissociation, which simply just means that the base is going to accept a proton and allow something else to dissociate. And this is going to equal to it's equilibrium constant, so it's the same as everything else, is then equal to our product divided by the reactant. So we have our conjugate acid here, and we have our OH minus concentration divided by our weak base. If we have our Kb value, we can then go forward and get pKb by using the P scale. That's going to be negative log of Kb. Why is this important to use? Because remember, the P scale allows us to have numbers that are just easier to use in calculations. Can I go further and just get the Kb value on its own? Yes. If given the pKb value, I can take 10 raised to the power of minus or negative pKb, and I can go ahead and get my Kb value. So again, our K value is going to help us understand if we have a strong base or a weak base. If we have a strong base, we know our Kb value should be really, really big because we're going to produce more of our products here. So you're going to have a higher amount of OH minus, you're going to have a larger Kb value, and if you have a larger Kb value, then that means you're going to have a smaller pKb. Okay, folks? We can do the same kind of trend and process with a weak base. A weak base, you're now going to have less of your products and more of your actual reactants. Therefore, you're going to have a lower amount of OH minus, you're going to have a smaller Kb value, and if you have a smaller Kb value, then you're going to end up having a larger pKb value. And so we can just run through a list of information that we would know from weak bases, okay? Now, for weak bases, there are going to be two main or two large classes for Bronson-Lowry bases that we are going to focus on. First is going to be the molecular species ammonia and the amines, okay, as one whole group. And then next we'll focus on the anions of weak acids. And so we'll be able to see and go through both of those as we go along. First, let's focus on the first, which is going to be ammonia and amines. And then next, we'll get into our anions of weak acids. Okay, so the first class is going to be ammonia and the amines. So ammonia is simply going to be NH3, and it represents the simplest type of a nitrogen-containing compound that we focus on, okay? And then we also have amine groups. So if you think of Chapter 20, yes, it's a throwback, right? But if we think of Chapter 20 and we think of what an amine is going to be a functional group that had all single bonds. So it's going to be an R group bonded to, which we know is starting with carbon here, bonded to the nitrogen, and of course, there's two hydrogens attached to it as well. Now, one big thing about the ammonia and amine group is that they have that lone pair nitrogen, and that's going to be what has the ability to accept the proton. That's why it's so important. Now, the second class we're going to get into is the anions of weak acid. Another way to think of that is just the conjugate base of a weak acid. So if I have my weak acid here, of course, I'm going to mix it with water. Then I'm going to create H2O plus because it's an acid. And I'm going to have A minus. This A minus is the conjugate base of that weak acid. And guess what? It's also considered a weak base that we can use in equilibrium calculation. But first, let's focus on ammonia and the amines. Okay, so first up, we have the molecular species ammonia, or NH3. And of course, we focus on NH3 Iron Man. He has a repulsor beam in his chest that has the ability to accept energy unless they accept a proton. That's the way we think of it, okay? And normally, when we take our NH3 and mix it with water, we end up disassociating to form NH4 plus and OH minus, okay? In other words, that NH3 is going to accept a proton and become the conjugate acid NH4 plus, and of course, have OH minus in there as well. The OH minus is going to tell us the strength of that particular base. Because we're in equilibrium, we know we're dealing with a weak base. So what does that mean? Most of the time, you're actually dealing with water and NH3 that has not accepted a proton yet, right? So we have to kind of keep that in mind. If we're thinking about even lab, all the time when you're going around, you're like, hey, where's the NH3? Where's the NH3 on the bottle? So you have your bottles, and what is on the bottle? We have NH4OH. And we put that on the bottle to help you just say, hey, we're specifically an aqueous solution. But in reality, when you're actually thinking about it, now that we have this layer of information, the bottle should simply read NH3. Why? Because when we're dealing with the weak base, we are mainly going to have mostly reactants, right? Not products, okay? So because of that, we're mainly going to have a lot of NH3 mixed around in water in the solution. And the Kb value for this overall reaction is 1.76 times 10 to the negative 5. So it's relatively small, right? And so, and I would say moderately small, right? So when I think about that, I'm like, okay, it's moderately small. In lab, it's just easier to write the NH4OH because a lot of times we're usually going to be using this entire reaction in equilibrium. Now, hopefully we can apply that information if we see this again in lab. So we have ammonia, which is going to represent our simplest N or nitrogen containing weak base, right? But if we were to replace each of these hydrogens with an organic R group, then we are creating now amines. So an amine from a functional group is just R, NH2. So if I just had an R group and NH2, that would be considered an amine because it still has that electron or lone pair rich nitrogen here to accept a proton. And if I was to replace another hydrogen and I'll have two R groups, I'll just have two R groups and H. Again, we still have the nitrogen that we need for the bond. And then finally, if I replace all the hydrogens with R groups, I'll have R3 and then nitrogen. You don't have to memorize all the little details here, but you need to understand that no matter how many R groups are around, we have a nitrogen that has a lone pair and has the ability to accept a proton by donating those electrons, right? It's like this nitrogen is going to donate electrons to a proton so that it can form a NH bond. And therefore, it's going to get rid of H plus in solution and then be left with OH minus and called basicity. So the key structural feature for this first group of weak bases is that they have the nitrogen that is going to have that lone pair of electrons that can bond the proton. Now what else? Well, since we already kind of have an idea of what weak bases are, we saw their Kb values, now we can start just thinking about how to answer some weak bases type of questions. So what do? It's going to be very similar to weak acid. That means we got to have a balanced equation, got to have a Kb value and or an expression, right? So sometimes we won't have the Kb value, we just simply have the expression. You're probably going to have a Rice table. You definitely got some assumptions that we can use similar to weak acids. And then you want to solve for the concentration of OH minus. So if you solve for the concentration of OH minus, which is going to tell you how much of that base was able to accept a proton, then you can go ahead and get our POH. If you have POH, you can go further to get pH. You also, if you already have the OH minus concentration, you can use KW to get H3O plus. So there's a lot that you can do in order to answer these equilibrium problems, very similar to what we already seen. Now let's talk about some of these tables over here. These are just some basic Kb values for a lot of these weak bases. So as you can see, we have ammonia here. It has its Kb value. We have methylamine, which is basically taking an R group here, an NH2, and it has its K value as well, or Kb value. They show me Kb and pKb. I'm just focused on Kb values here. They also show me a reaction to show that this weak base is going to be mixed with water. So sometimes these tables can be very useful for all my visual folks out there. Also, I want to show you this methylamine, which is going to be your R group and NH2 here. This methylamine mixed with water. Here, the nitrogen is going to donate its lone pairs to this hydrogen to form a nitrogen-hydrogen bond here. And then, of course, they're going to form our methyl ammonium. And then what is left over, our OH minus, which is going to help us with basicity. Now, let's go ahead and apply our little strategy and technique for these weak-base equilibrium problems. Okay, this says dimethylamine, CH32, NH. That means we have two R groups, and then we have NH here. A key intermediate in detergent manufacture has a Kb value of 5.9 times 10 to the negative 4. What is the pH of a 1.5 molar CH3,2NH solution. All right, folks, so we're given our overall weak base, we're given our KB. They want us to find the pH, and we're given an initial amount for our overall weak base. Now, how can I know this is a weak base? Well, one, it contains nitrogen. That's the only one we've seen thus far, right? So it contains nitrogen, and we know that nitrogen has the ability to accept a proton. So all we need to do is read the overall question, gather necessary expressions and relationships, and make those assumptions, folks. So let's go ahead and do it. First things first, get a balanced chemical reaction where we're going to mix this base with water to produce our conjugate acid and, of course, OH minus. So here I have my CH3,2NH plus water is going to be in equilibrium to form CH3NH2 plus. So all we have to do is just add a charge because we're adding a proton, right? And so then what's left over? OH minus. And as you can see, I've already set up my Rice table because I already know I'm in equilibrium and I'm already thinking, hey, I've done the weak acids before. This couldn't be that bad. What's the next thing I need to do? I need to get my KB expression. So using the reaction here, I'm going to take my product divided by my reactant. We know that water doesn't do anything. So we have 5.9 times 10 to the negative 4. As you can see, because our KB value is small, we can assume here. What else could I have done? I could have taken my initial amount of 1.5 and divided by my KB. And as long as it's over 400, we know we can make an assumption. And guess what, folks? It is. Next, I'm going to go ahead and fill out my Rice table. So initial is going to be 1.5 molar here. You know, water doesn't matter. This is going to be 0, 0. This is minus X. This is plus X, plus X. So we know our equilibrium is just X and X here. That means if I solve for X, I can solve for the OH minus concentration. If I know my OH minus concentration, I can get POH. If I know my POH, I can solve for pH, which is what the question asks, right? Next, we can go ahead and fill out our equilibrium amount. So we're going to have 1.5 molar minus X here. Now, the question becomes, can I make an assumption? We already declared that was true. We can make an assumption. So I'm going to get rid of the minus X here. Now I can go ahead and fill out my KB. And it's going to be 5.9 times 10 to the negative 4 is equal to X squared divided by 1.5 molar. So let me go ahead and erase this, and then we'll solve for X. Once we have X, we'll have our OH minus, and then we'll go from there. Okay, so we have our X squared divided by 1.5 because we can make that assumption. We're going to take our 1.5 and cross multiply it with the KB value, 5.9 times 10 to the negative 4. Once I cross multiply those in my calculator, I get 8.85 times 10 to the negative 4. So to solve for X, I'm going to take the square root of both sides, and then I'm going to get X is equal to 3.0 times 10 to the negative 2, which is going to be the concentration of our OH minus species. Now that I have the concentration of OH minus, I can solve for POH. So my POH is going to be negative log of my OH minus concentration. So that's negative log of 3.0 times 10 to the negative 2. This is equal to 1.52 for my POH. Now, how can we verify it's only 2 decimal places? Well, because we only have 2 decimal places for our concentration. And that's because we have 2 decimal places for our overall numbers that we're giving to. Okay, so 2 decimal places all around for 6B. Now that I have my POH value, I can say pH is equal to 14 minus 1.52, which is going to equal 12.48, which is my answer. All right, folks, so that is how I approach this question. Could you have gotten the OH minus concentration and then use KW here? Yes, you could have. You definitely could use your OH minus concentration, plug it in here, and then solve for H3O plus. Once you had H3O plus, you can simply solve for pH. So that's another option. I chose to do it this way this time. So far we see, because we put so much effort in understanding weak acids and all their calculations, by the time we get to weak bases, layering the information and getting an understanding of how to approach it becomes easier for us.